Einstein called it impossible. NASA called it fantasy. But in April of last year, a small team of physicists in Manhattan published equations that proved them both wrong. They found a loophole, the glitch in reality that lets you travel to another star without breaking the speed of light, without infinite fuel, and without the crushing G-forces that should kill every crew aboard. This isn't science fiction anymore. It's published mathematics, peer-reviewed and sitting in the open literature, waiting for someone to build it before we break the universe. Hit subscribe. It keeps the lights on. Here's the wall. The nearest star beyond our sun sits 25 trillion miles away. That's 25 with 12 zeros. So vast your brain physically cannot visualize it. We didn't evolve to understand distances like this. So try this. Light, the fastest thing in existence, circles Earth 7 times in 1 second. In a single snap of your fingers, a photon could race from New York to Tokyo and back. Yet even at that incomprehensible velocity, a beam of light leaving Proxima Centauri right now won't touch Earth until 2029. For years of photons racing through perfect vacuum just to reach our doorstep. And we don't have light-speed ships. We have Voyager. Voyager 1 has been sailing for nearly 50 years. It's the farthest man-made object ever flung into the dark, traveling at 38,000 miles per hour, 19 times faster than a bullet. Fast enough to reach the moon in 7 hours, Mars in weeks. But pointed at Proxima Centauri, the math is brutal. 70,000 years. 70 millennia of silent drifting before it would pass that star. By then, humanity will have evolved into something unrecognizable or vanish entirely. And that's just the closest one. Sirius, the bright dog star, 150,000 years. Betelgeuse, so distant that a Voyager-class probe launched today would arrive only after our sun has swollen into a red giant and consumed the Earth. You cannot bridge that gap with bigger rockets. This is an engineering problem. It's a prison built by physics itself. Every rocket is a slave to the rocket equation, a tyrant of exponential mathematics. To go farther, you need fuel. But fuel has mass. Mass needs more fuel to accelerate, which adds more mass, which needs more fuel. The Saturn V burned 3,000 tons of kerosene and oxygen in 2.5 minutes just to push 3 humans to the moon. Proxima Centauri is 100 million times farther. To reach it in a human lifetime, using chemical rockets, you'd need more hydrocarbons than exist on Earth. You'd need to drain Jupiter's atmosphere, strip every organic molecule from Saturn's moons, and still fall short by orders of magnitude. The equation doesn't care how hard you try. So engineers look for cheats. Nuclear pulse propulsion, riding the shockwaves of atomic bombs, could get you to 3% light speed. Fusion, the power of stars, remains decades away from practical use. Antimatter is perfect on paper, 100% mass-to-energy conversion, but we manufacture it in billionths of a gram per year. Solar sails could push tiny chips to 20% light speed, but scaling that to human crews requires lasers draining the power grid of continents. None of it breaks the real ceiling. See, the speed of light. Einstein's 1905 special relativity proved that as you approach light speed, your mass balloons toward infinity. At 99% of c, you weigh 7 times more. At 99.9%, 22 times more. To actually hit light speed requires infinite energy, and infinite energy does not exist. The cosmic speed limit is absolute. The universe is sealed shut, or so we thought, until a 28-year-old physicist in Wales asked a heretical question. In 1994, Miguel Alcubierre was a postdoc at Cardiff University with a weakness for Star Trek. While other physicists dismissed warp drive as Hollywood fantasy, Alcubierre treated it as a homework assignment. He opened Einstein's field equations, the mathematical scripture describing how mass curves spacetime, and asked, what shape would spacetime need to have to move a bubble faster than light without anything inside that bubble actually exceeding light speed? The loophole was hiding in plain sight. Einstein's limit applies to objects moving through spacetime. It says nothing about spacetime itself moving. We know space can outrun light. The universe expands. Distant galaxies recede from us faster than 186,000 miles per second. Not because they're moving through space, but because the space between us is stretching. Like ants on a rubber sheet being pulled apart, they ride the geometry. No speed limit applies to the sheet itself. Alcubierre imagined surfing that expansion. Compress spacetime in front of ship, expand it behind, and let the ship ride the wave. He constructed a metric, a mathematical recipe for spacetime geometry that described a bubble. Inside, flat space, normal physics, zero-G forces. Outside, flat space, the rest of the universe. But at the boundary, the fabric of reality pinches and stretches. The bubble surfs a wave of distorted geometry, arriving at Proxima Centauri in weeks, while the passengers inside never felt acceleration. When he published The Warp Drive, Hyperfast Travel Within General Relativity, in 1994, the physics world shuddered. The math was perfect. It was a valid solution to Einstein's equations. But the price tag was cosmic. The bubble required exotic matter with negative energy density, stuff that repels gravity, and early calculations suggested you'd need more negative mass than the entire observable universe. The idea languished as a curiosity until 1999, when Chris van den Broek in Belgium found a geometric hack. By shrinking the bubble's exterior to the size of an atomic nucleus, while keeping the interior spacious, he slashed the energy requirement by 20 orders of magnitude, down to merely the mass of Jupiter. Still impossible, but breathing room. Then in 2011, NASA physicist Harold Sunny White redesigned geometry again. A toroidal warp, a donut-shaped bubble with thick walls, dropped the requirement to roughly 700 kilograms, the mass of a motorcycle. Suddenly, this wasn't cosmological, it was industrial. But 700 kilograms of what? Exotic matter remained fictional. The barrier persisted until 477 Madison Avenue. Inside a private research lab in Midtown Manhattan, a small group called Applied Physics treated warp drive not as theory, but as engineering. Led by physicists including Alexei Bobrick and Johnny Martiri, they first classified every possible warp geometry, proving that subluminal warp drives, slower than light, might not need negative energy at all. Then, on April 29, 2024, they published a paper that changed everything. Classical and Quantum Gravity, Volume 41, Issue 9, Constant Velocity Physical Warp Drive Solution, led author Jared Fuchs, alongside Christopher Helmerick, Alexei Bobrick, and Johnny Martiri. They found it, a warp bubble that requires no exotic matter, zero negative energy, a solution that uses only positive mass, normal matter, the stuff we can actually touch and manufacture, arranged in a specific geometry of shells and velocity gradients. The ship still rides a wave of contracting and expanding space-time, but the energy source is real, physical, and achievable. The mathematics prove that a bubble of flat space-time can be propelled at constant velocity through the universe using nothing more than classical energy distributions. No infinite fuel, no violation of relativity, just an engineered ripple in the fabric of reality, carrying human passengers to another star in years instead of millennia. The door is open. The equations are solved. All that remains is to build the ship. Christopher Helmerick, Alexei Bobrick, Luke Sellers, Johnny Martiri, the entire applied physics team pulling together, focus on a single problem. When their paper dropped in Classical and Quantum Gravity on April 29, 2024, what it claimed was extraordinary. The authors presented a warp drive solution that satisfies all the classical energy conditions. All of them. The weak energy condition, the null energy condition, the dominant energy condition, the strong energy condition. These aren't bureaucratic rules. They are the mathematical criteria that ordinary matter satisfies and that exotic matter violates. They emerge from quantum field theory and have been tested against countless observations. Violating them usually means you're dealing with something unphysical, something that doesn't exist in nature. The Fuchs warp drive violates none of them. No negative energy anywhere in the structure. No exotic matter. No violations of any physical principle observed in the real universe. The design combines two elements. First, a stable matter shell with a specific density distribution built entirely from positive energy material, the kind of matter that exists throughout the universe. Ordinary baryonic matter, protons, neutrons, electrons, arranged in specific configurations. Nothing exotic. nothing that requires new physics to produce. Second, a shift vector distribution. This is a mathematical feature of the space-time metric. It describes how different parts of space are moving relative to each other. In the Fuchs design, the shift vector creates a flow pattern that mimics the Alcubierre geometry. Space compresses slightly ahead of the bubble, expands slightly behind it. But the compression and expansion are driven by the distribution of ordinary matter in the shell, interacting with the shift vector structure. Together, the shell and the shift vector produce the warp effect. A region of flat space moves through the surrounding universe, carrying anything inside it along for the ride. The paper uses software called Warp Factory to evaluate the design numerically. Warp Factory is a tool the applied physics team developed and released publicly, written in MATLAB. It allows researchers to input any proposed warp metric and calculate its properties. The stress energy tensor, which tells you what kind of matter would be needed, the energy conditions, which tell you whether that matter is physical, the curvature scalars, which describe how strongly space-time is bending, and visualizations that let you see the geometry. When you run the Fuchs metric through Warp Factory, the output is clean. The visualization shows blue everywhere. Blue indicates positive energy density, the kind that matches ordinary matter. Black lines show momentum flux, the internal structure of how energy and momentum flow through the bubble. Nowhere in the entire visualization does red appear. Red would indicate a violation of the energy conditions, a region requiring exotic matter. The Fuchs warp drive has no red. It's entirely blue, entirely physical, entirely consistent with known physics. Fuchs explained the breakthrough in interviews and press releases. Prior warp drive models, he said, require matter and energy content that was unphysical, features nobody has ever observed in nature. The new approach avoided that by adding positive energy to the solution, while keeping as much of the warp effect as possible. When physicists talk about positive energy, they mean phenomena like light, ordinary matter, and antimatter, all of which exist naturally, all of which we can detect, measure, and in some cases produce. The solution also uses gravity itself as part of the warping mechanism. Gravity is already a manifestation of curved spacetime, a sufficiently dense and precisely shaped distribution of ordinary matter curves space around it. That curvature, when combined with the shift vector structure, produces the warp bubble. No exotic physics existed that didn't require anything the universe refuses to provide. The physics community reacted with cautious optimism. Mainstream physicists acknowledged that the solution was mathematically valid. It satisfied the energy conditions as claimed. It represented genuine progress. But skeptics pointed out that a warp drive using only positive energy, while novel, doesn't solve the interstellar travel problem if it can't go faster than light. And the Fuchs design cannot, because the paper includes a caveat that headlines often buried. This solution is explicitly subluminal. The bubble moves at a constant velocity, and that velocity is less than the speed of light. Subluminal means below light speed. The Fuchs warp drive does not enable faster than light travel. It does not let you reach Proxima Centauri in days or weeks. It does not break Einstein's cosmic speed limit. What it does is prove that warp spacetimes as a class of solutions are not inherently dependent on exotic matter. At least some warp configurations can be built from ordinary positive energy materials, using physics we already understand. Fuchs was careful about this limitation in every interview. He told reporters plainly that this concept will not deliver Star Trek-style rapid interstellar transport. What it delivers, he said, is the warp effect itself, the ability to accelerate passengers without subjecting them to G-forces, using regular matter. And that capability, even at subliminal speeds, could lead to other interesting applications. Let me explain why this matters. A subliminal warp bubble traveling at, say, 90% of the speed of light would take about 4.7 years to reach Proxima Centauri as measured by outside observers. For the crew, due to time dilation, the subjective experience will be shorter, roughly 2 years. That's still a long trip. It's not the weeks or months of science fiction, but it's no longer generational. It's within the career span of a single astronaut. Someone could volunteer for the mission, make the journey, and return within their working lifetime. More importantly, a subluminal warp drive transforms travel within the solar system. Right now, A trip to Mars takes about 6 to 9 months, depending on the alignment of planets. The spacecraft has to coast most of the way because sustained thrust will require too much fuel and would crush the crew. A Mars mission is a slow, careful ballet of orbital mechanics. Launch windows open only every 26 months. The trajectory is fixed months in advance. Mid-course corrections are limited. It's cumbersome and restrictive. A warp bubble changes everything. Inside the bubble, space is flat. The crew experiences no acceleration. Even if the bubble itself is accelerating rapidly, the passengers feel nothing. A warp ship could fire its engines continuously, accelerating to a significant fraction of light speed. Coast briefly, then decelerate just as hard. The entire trip to Mars could be measured in days instead of months, possibly hours, if you push the acceleration high enough. The crew would arrive fresh, unaffected by the brutal forces that would normally accompany such a journey. The same logic applies to everywhere else in the solar system. Jupiter, currently a multi-year voyage, becomes a matter of weeks. Saturn, Neptune, the Kuiper Belt, all within reach of short-duration missions. You could send crewed expeditions to study these worlds up close without committing decades of an astronaut's life to the journey. And there's a safety benefit most coverage overlooks. A subluminal warp bubble does not generate a horizon at its leading edge. When a bubble moves faster than light, the front edge is receding from the ship's interior faster than any signal from inside could catch up. This creates what's called an event horizon, a boundary beyond which the interior cannot send information. Horizons are bad news. They produce Hawking radiation, a quantum effect that would irradiate the crew. They prevent steering because you lose causal contact with your own leading edge. They trap particles which get released as a devastating beam when the bubble shuts off. All of these problems are features of superluminal travel. Specifically, a subluminal bubble doesn't cross the light barrier. No horizon forms, no Hawking radiation, no loss of control, no particle beam weapon. The ship remains in causal contact with its entire structure. The pilot can steer, adjust course, and decelerate safely. The physics permits it. The materials are ordinary. The crew is protected. And for the first time, there's an actual engineering path connecting our current technology to eventual warp capability. Not a path we can walk tomorrow. Not even a path we can walk this century, but a path. The engineering challenges are still enormous. Building a matter shell with the density profile the Fuchs design requires is far beyond our current material science. The shell would need to maintain its shape against gravitational stresses, thermal fluctuations, and the dynamic forces of acceleration and deceleration. Current high-strength materials, things like carbon fiber composites and advanced steel alloys, can handle pressures up to a few gigapascals. The warp shell would need to handle stresses thousands of times higher without deforming or failing. We don't have materials that can do that. We might not have them for centuries. The energy requirements are also staggering. Even though the Fuchs design doesn't need exotic matter, it still needs energy, lots of it. Accelerating a massive shell of ordinary matter to 90% of light speed requires energy inputs comparable to significant fractions of global power production. We're talking terawatts sustained over hours or days. That's energy on a scale we've never attempted. The instrumentation to test even small-scale warp effects doesn't exist yet. Before anyone builds a full-scale warp ship, someone needs to demonstrate that the effect works at laboratory scale. That means building interferometers sensitive enough to detect space-time curvature around benchtop experiments. Current instruments can measure gravitational waves from colliding black holes billions of light years away, but measuring static local curvature from a small matter distribution is a different problem entirely. It requires precision we haven't achieved. Nobody is building a warp drive this decade or next. Probably not this century. But the physics allows it. The math is clean. The materials are ordinary, even if we can't shape them properly yet. And there's a research community actively working on the problem. In early 2026, less than 2 years after the Fuchs paper, another study suggested the next refinement might already be on the horizon. A follow-up paper from the applied physics team and collaborators revisited the warp drive metric families with more sophisticated mathematical analysis. The central finding was that space-time can bend further than earlier models assumed. Previous calculations had made certain assumptions about how the warp bubble geometry must blend into the surrounding universe, assumptions based on mathematical convenience and computational tractability. When those assumptions were relaxed, the equations revealed a wider range of possible curvature profiles. Some of the newly identified profiles correspond to warp drives that use even less energy than the 2024 Fuchs design. A few might allow superluminal operation with significantly reduced exotic matter requirements. Reduced, not eliminated, but reduced enough that the problem might shift from impossible to merely extraordinarily difficult. The paper didn't claim to have solved the faster-than-light problem. What it claimed was that the solution space is larger than anyone had been exploring. For 30 years, warp drive research had been narrowing, eliminating candidate designs one by one as they failed energy conditions, stability tests, or other physical criteria. The new result argued that some of those eliminations were premature, that researchers have been searching a subset of the actual solution space, and that reopening the discarded regions might yield hybrid designs combining the best features of multiple approaches. Research groups at universities in Germany, Australia, Japan, and the United Kingdom immediately began running simulations using Warp Factory and other numerical tools to evaluate the newly identified metric families, checking which ones satisfy energy conditions, which ones are stable against small perturbations, which ones could plausibly be built with materials that might exist. As of this recording, no paper has delivered a superluminal warp drive that passes every test and uses only ordinary matter. The superluminal barrier remains. But what has changed, subtly but significantly, is the attitude of the broader physics community. Throughout the 1990s and 2000s, warp drive research was fringe, tolerated in the literature because the math was valid, but not taken seriously as a path to real technology. Conferences didn't feature sessions on it. Graduate students didn't write dissertations on it, without raised eyebrows from their committees. Funding agencies didn't support it. By the mid-2020s, that changed. Papers on warp drive appear regularly in Classical and Quantum Gravity, Physical Review D, and other top-tier journals. Conference sessions on advanced propulsion draw large audiences. NASA maintains an interest, even if Eagle Works is no longer as active as it was. Private organizations like Applied Physics publish openly and collaborate with academic researchers. Graduate students cite warp metrics in their work without professional stigma. The field has moved from mathematical curiosity to legitimate engineering problem. The engineering might still be centuries away, but it's engineering, not fantasy, and that distinction matters. There is, however, one aspect of superluminal warp drive that needs to be addressed. The reason faster-than-light remains so difficult has everything to do with what happens at the front edge of the bubble when it crosses a light barrier. When a warp bubble moves faster than light, it creates something called a horizon. A horizon is a boundary in space-time beyond which information cannot pass in certain directions. The most familiar example is a black hole event horizon. At a black hole's event horizon, space-time is falling inward faster than light can propagate outward. Anything crossing that boundary cannot escape. Not because it's being pulled by some overwhelming force, but because the geometry of space-time itself has changed such that all future-directed paths point inward. There's no direction you can move that leads back out. A superluminal warp bubble generates a similar structure at its leading edge. The front wall of the bubble is moving outward faster than light, which means any signal sent from inside the bubble toward the front edge can never catch up. The front edge is receding faster than the signal can propagate. This creates a causal disconnect. The ship's interior is cut off from its own leading edge. A radio signal sent from the pilot's seat toward the front of the bubble would never arrive. The signal would chase the front wall forever, never catching up, never influencing what happens there. From a navigation standpoint, this is catastrophic. During the voyage, the ship cannot steer. It cannot adjust course. It cannot transmit any information ahead of its position. The bubble must be aimed correctly before launch, because once it's moving at superluminal speed, the crew has no causal access to the region of space they're heading toward. Any error in the initial trajectory cannot be corrected mid-flight. Any obstacle in the path cannot be avoided. The ship simply plows forward on whatever vector it was set to, unable to respond to changing conditions. It gets worse. A superluminal warp bubble also cannot be stopped from inside. To decelerate, the bubble would need to change its own geometry, shift the distribution of matter or energy in the warping region. But doing that requires sending signals from the ship's interior to the bubble boundary. And if the bubble is moving faster than light, those signals cannot reach the leading edge. You're locked in. The only way to stop is to have external infrastructure at the destination. Pre-positioned equipment set up by an earlier mission that can collapse the bubble from outside, or some kind of autonomous mechanism embedded in the bubble wall itself, programmed to shut down after a certain duration. Neither option is reassuring. The pilot sitting in the control seat has effectively become a passenger, watching the universe blur past through windows that no longer obey normal causality. Some theorists have proposed workarounds. One idea involves oscillating the bubble, switching it on and off at high frequency, so the ship has brief moment of causal contact with the outside universe between warp pulses. The math for this exists in certain models, but introduces severe stability problems. A bubble that keeps collapsing and reforming might emit catastrophic bursts of radiation with each cycle. The energy release could be enough to vaporize the ship. Another idea is to simply accept the limitation and design missions around it. Warp drives become long-range ballistic devices. You aim them carefully, launch them, and hope they arrive where you pointed them. For pre-planned routes between established destinations, this might be workable. For exploration, it's essentially useless. The horizon problem doesn't prove warp drive is impossible. It proves that superluminal warp drive, if it works, would be a fundamentally different kind of vehicle than anyone imagined. Not a steerable starship that you pilot like an airplane, but a ballistic projectile that you aim and fire with no ability to change course once launched. And there's a second consequence of the horizon that's even more dangerous: radiation. In 1974, Stephen Hawking published a result that shocked the physics community. He proved that black holes emit radiation. Before Hawking's work, everyone assumed black holes were perfectly black. No light escapes, no heat radiates away. They're cold, dark, silent objects that only absorb and never emit. Hawking showed that quantum mechanics changes the picture. Near the event horizon of a black hole, virtual particle pairs constantly pop into existence from the vacuum. Normally, these pairs annihilate almost immediately and disappear. But near a horizon, something different happens. One particle of the pair can fall into the black hole while the other escapes. The escaping particle becomes real, carrying energy away. From the outside, it looks like the black hole is radiating. This is called Hawking radiation. The temperature of the radiation depends on the size of the black hole. Larger black holes emit cooler radiation. Smaller black holes emit hotter radiation. A black hole the mass of our sun would have a Hawking temperature of about 60 nanokelvin, 60 billionths of a degree above absolute zero, far too cold to detect against the cosmic microwave background. But a smaller black hole, say one the mass of a mountain, would radiate at higher temperatures, and a microscopic black hole would be incredibly hot. Now apply this same physics to a superluminal warp bubble. The bubble's leading edge forms a horizon, not exactly like a black hole horizon, but similar in irrelevant ways. It's a boundary where causal structure changes, where future-directed paths cannot cross back. And wherever you have a horizon, Hawking radiation should appear. Near the front wall of the superluminal warp bubble, virtual particle pairs pop into existence. One particle falls forward into the region the bubble is moving into. The other particle falls backward into the ship's interior. From the crew's perspective, particles are raining in from the leading edge, a constant stream of radiation generated by the horizon geometry itself. The problem is that warp bubbles are small, much smaller than astrophysical black holes, and radiation temperature scales inversely with horizon size. Smaller horizon means hotter radiation. A superluminal warp bubble moving at, say, 10 times the speed of light would have an effective horizon radius on the order of feet or tens of feet. Theoretical calculations suggest the Hawking temperature of such a horizon could be thousands or even millions of Kelvin, hotter than the surface of the sun. The crew inside the bubble wouldn't just feel warm. They'd be bathed in high-energy particles pouring inward from the front wall, X-rays, gamma rays, possibly even more energetic radiation. The intensity would be lethal within seconds. A paper published in 2009 by physicists at the University of Sydney worked through this calculation in detail. Their conclusion was stark. Any macroscopic superluminal warp bubble would generate Hawking radiation at the leading edge intense enough to kill the crew almost instantly. The faster the bubble moves, the hotter the radiation becomes. There's no escape. No shielding would help because the radiation is being generated inside the bubble between the ship and the front wall. Putting shielding between the crew and the source will require disrupting the bubble geometry itself, which would collapse the warp drive. Are there ways around this? Possibly. If the bubble wall could be shaped very carefully, some of the radiation might be redirected. Focused away from the ship's interior, out through the sides or back of the bubble. Alcubierre himself has speculated that quantum gravity corrections, the still unknown physics that unifies general relativity with quantum mechanics, might modify Hawking radiation in ways that soften the effect, at the scales where quantum gravity becomes important, roughly the Planck length of 10 to the power of negative 35 meters. Space-time itself might behave differently than classical general relativity predicts. Those modifications could change how horizons emit radiation. But this is speculation. We don't have a theory of quantum gravity. We don't know whether it would help or make things worse. There's also the subluminal escape clause. If the warp bubble moves slower than light, no true horizon forms. And without a horizon, there's no Hawking radiation. This is yet another reason why subluminal warp drives, like the Fuchs design, are more practical. They avoid the radiation problem entirely by staying below the threshold where horizons appear. The Hawking radiation issue remains one of the most serious objections to superluminal warp travel. It's not an engineering challenge that better materials or more energy could solve. It's built into the structure of space-time and quantum field theory. A faster-than-light bubble creates a horizon. A horizon emits radiation. The radiation kills the crew, unless something about our understanding of physics changes. This might be an absolute barrier. There's one more hazard worth discussing. Something that happens during the voyage itself, involving the matter the bubble encounters along the way. Interstellar space is not truly empty. It's thinly populated. Hydrogen atoms, about 1 per cubic centimeter on average. Helium atoms much rarer, occasional grains of cosmic dust, stray electrons and ions, cosmic rays, high-energy particles from distant supernovae. For a spacecraft moving at conventional speeds, this sparse medium is negligible. Voyager has been traveling through it for 50 years without issue. But for a warp bubble moving at hundreds or thousands of times the speed of light, this thin gas becomes a weapon. The physics was worked out in a 2012 paper by Brendan McMonagle, Geraint Lewis, and Philip O'Byrne. The team asked, what happens to the interstellar medium when a superluminal warp bubble plows through it? The answer was alarming. As the bubble moves forward, hydrogen atoms and dust particles in its path don't pass cleanly through. They get caught, trapped in the warp geometry at the leading edge. The compression of space-time accelerates these particles to enormous energies. They accumulate, building up a reservoir of matter, traveling with the bubble. The longer the voyage, the more matter accumulates. A trip of several light years would sweep up billions upon billions of particles, each one carrying energy proportional to the bubble's velocity. When the bubble finally arrives at its destination and shuts down, all that accumulated matter gets released. The trapped particles blast outward from the ship's position in a tightly focused beam. The beam travels in the direction the ship was heading, directly toward the destination. The energy in this beam, according to McMonagle and colleagues, could be equivalent to hundreds of thousands of solar masses worth of kinetic energy concentrated into a narrow cone. Anything in that cone would be annihilated. A warp ship arriving at Proxima Centauri wouldn't land gracefully. It would sterilize the star system. Any planets in the beam's path would have their atmospheres stripped away, their surfaces scorched down to bedrock, possibly vaporized entirely if the beam was intense enough. The ship itself would survive. It was inside the bubble, shielded from a release. But the civilization that sent it would have just committed an act of interstellar destruction, even if unintentional. This is sometimes called the warp drive genocide problem, and it's not hypothetical. The math is straightforward. The effect scales with distance traveled and particle density encountered. Even the extremely low density of the interstellar medium, accumulated over light years, produces a devastating result. Some proposed solutions involve modifying the bubble geometry to deflect particles rather than trap them, a hydrodynamic shaping of the front wall that guides incoming matter around the sides of the bubble. Other proposals suggest ending the voyage far from the destination in empty space and letting the beam disperse harmlessly before approaching under conventional propulsion. Both ideas add complexity. Both introduce new potential failure modes. For mission planners, the particle accumulation problem means superluminal warp ships couldn't approach inhabited star systems directly. They'd need arrival protocols, long deceleration zones, careful alignment to aim the exit beam away from anything valuable, advance warning to civilizations at the destination, assuming they exist and have the technology to receive messages. It's yet another complication stacked on top of the exotic matter requirement. The horizon problem, the Hawking radiation, and the steering limitations. Between all of these issues, the original Alcubierre warp drive started looking less like a sleek starship and more like an uncontrollable weapon that happens to transport cargo, which raises a question. If warp drive has all these problems, is there a different approach to faster-than-light travel that avoids them? There is. Sort of. Instead of warping space around a ship, imagine cutting a tunnel directly through space itself. A shortcut, a path connecting two distant points along a route shorter than the surrounding universe allows. The ship doesn't need to move fast at all. It walks through the tunnel, emerges light years away, moments later. This is called a wormhole. And like warp drive, wormholes emerge from Einstein's equations as mathematically valid solutions. The basic concept was first described by Albert Einstein and Nathan Rosen in 1935. They were studying the interior geometry of black holes and discovered that the mathematics permitted a bridge, a connection between two otherwise separate regions of space-time. The Einstein-Rosen bridge, as it became known, was a feature of the Schwarzschild black hole solution. It linked the black hole's interior to another region, possibly another universe entirely, or a distant part of our own universe. Early physicists treated this as mathematical curiosity. The bridge wasn't traversable. It would collapse too quickly for anything to pass through. And even if you could enter it, you'd be crushed by tidal forces before reaching the other side. The situation changed in 1988. Kip Thorne, a theoretical physicist at Caltech, who would later win the Nobel Prize for the first detection of gravitational waves, published a paper with collaborators Michael Morris and Ulvi Yurtsever. The title was Wormholes in Spacetime and Their Use for Interstellar Travel. The paper was partly inspired by a request from Carl Sagan. Sagan was writing the science fiction novel Contact and wanted a scientifically plausible way for his characters to travel faster than light. He asked Thorne if there was any mechanism permitted by general relativity. Thorne took the question seriously. His team's result was striking. Traversable wormholes, meaning wormholes you could actually travel through without being destroyed, were valid solutions to Einstein's equations. Provided certain conditions were met, a spacecraft could enter one mouth of the wormhole, travel through a short throat connecting the mouths, and emerge in the exit potentially light years away. The journey through the throat could take minutes or hours. The two mouths could be separated by any distance across the galaxy if you wanted. From the outside, the trip would appear instantaneous or nearly so. The ship disappears into one mouth, reappears in the other, potentially before any light signal following the normal route could make the journey. Think of space-time as a sheet of paper. Normally, to get from one point to another, you travel across the surface. A wormhole is like folding the paper so the 2 points touch, then poking a hole through both layers. The hole creates a shortcut. The distance through the hole is much shorter than the distance across the surface. The trip through the wormhole doesn't exceed light speed locally. A photon racing through it still move at 300,000 kilometers per second through the throat. But the shortcut makes the effective travel time much less than going a long way around. An observer watching from outside would see a ship enter one mouth and emerge in the other almost instantly. Potentially faster than light could have made the trip through normal space. Unlike warp drive, wormholes don't involve moving through space at all. There's no bubble racing across the universe, no compression or expansion of the surrounding geometry. The tunnel exists as a fixed structure, a permanent feature of space-time with entry and exit points that don't move. The ship simply flies through, In principle, you could position the mouths anywhere in the universe. One mouth in Earth orbit, the other in orbit around a planet at Alpha Centauri. Step through one, emerge from the other. The engineering problems, however, make warp drive look simple by comparison. Kip Thorne's 1988 paper laid out the requirements for a traversable wormhole. The list is demanding. First, the wormhole must have no event horizon. An event horizon is a one-way boundary. Cross it and you can't come back. If a wormhole had an event horizon, travelers entering would be trapped. Most naturally occurring wormhole solutions, including the Einstein-Rosen bridge, have horizons. They're not traversable. A usable wormhole requires specific geometry where both mouths are open, accessible, and connected with no barriers. Second, the throat must be wide enough for a spacecraft. Obvious, but important, in a narrow throat, tidal forces would be extreme. The difference in gravitational pull between the nose and tail of the ship could stretch the vehicle apart. Thorne calculated that for a human-scale spacecraft to transit safely, the throat needs a minimum radius of several miles. Anything smaller, and the tidal stresses would destroy the ship. Third, the transit time must be reasonable. A wormhole where time passes much faster or slower inside than outside is problematic. Thorne showed that throats with ordinary local time flow are possible if the matter holding the wormhole open is arranged correctly. Fourth, and most critical, the wormhole must be held open. This is where the physics becomes impossible with current knowledge. Ordinary matter, the kind that makes up stars, planets, and everything we interact with, curves space-time inward. Gravity is attractive. It pulls. A wormhole throat, being a tunnel through space-time, naturally wants a pinch shut under this attractive force. It's unstable. To keep it open, you need something that pushes outward, something that creates repulsive gravity. Thorne identified what's required: exotic matter, matter with negative energy density, the exact same substance Alcubierre's warp drive needs, the stuff that might not exist, and for a wormhole, you need a lot of it. Thorne estimated that holding open a wormhole large enough for a mile-scale spacecraft will require exotic matter comparable to the mass of a large planet, arranged in a shell around the throat in a precise geometric configuration. The setup is delicate. Any fluctuation in the exotic matter distribution could cause the throat to collapse. And if the throat collapses while a ship is inside, the ship is crushed out of existence. Compare this to warp drive. A warp bubble needs exotic matter in a shell around the ship. The shell is moving through space. Once it's configured and accelerated, it just maintains its shape. Modern designs like the Fuchs solution have eliminated the exotic matter requirement entirely for subluminal cases. A wormhole is fundamentally different. The exotic matter isn't decorative. It's structural. It's holding the wormhole throat open against constant gravitational pressure. Remove the exotic matter for even a microsecond and the throat collapses. The quantity required is also larger. Thorne's planet mass estimate applies to a relatively modest wormhole. Scaling up to larger apertures or longer connections increases the requirement. Some calculations suggest a wormhole suitable for regular interstellar traffic would require exotic matter equivalent to several stars' worth of mass, all concentrated in the throat region. If ordinary matter were packed that densely, it would collapse into a black hole. Exotic matter by definition behaves differently, but the geometric demands are severe regardless. There's also a stability problem. Researchers have analyzed perturbations to wormhole geometries, small disturbances, tiny fluctuations in the exotic matter distribution. Most configurations are unstable. A perturbation causes a throat to start collapsing. Once collapse begins, it proceeds catastrophically. The wormhole pinches shut in a fraction of a second. Anything inside is destroyed. Making a wormhole stable requires incredibly precise balance, conditions that may not be physically achievable. Compare this to subluminal warp drive, where the applied physics team demonstrated a design using only positive energy. No analogous result exists for wormholes. Every traversable wormhole solution anyone has written down requires exotic matter in the throat. The no-go theorems in this area are stronger than for warp drive. While subluminal warp might be possible with known physics, wormholes appear to require genuinely new physics, a breakthrough we haven't made. For mission planners comparing the two approaches, the choice is clear. Warp drive, at least in subliminal form, connects to existing physics and plausible future material science. Wormholes require a fundamental advance in our understanding of matter and energy. Both are faster-than-light concepts, at least in principle. Only one has a visible path forward. But there is one place in the universe where negative energy has been confirmed to exist, and it might be the key to understanding whether either technology could ever be real. In 1948, a Dutch physicist named Hendrik Casimir was working at the Philips Research Laboratory in Eindhoven, Netherlands. He was studying the quantum behavior of electromagnetic fields, and he predicted something strange. Two uncharged parallel metal plates placed very close together in a vacuum should attract each other, not because of gravity, which is far too weak at such small scales, not because of static electricity. Since the plates are neutral, the attraction, Casimir said, would come from the quantum vacuum itself. His prediction was based on quantum field theory. The theory says that empty space isn't truly empty. It seethes with activity. Virtual particles constantly pop into existence in pairs, exist for a tiny fraction of a second, and annihilate. These fluctuations happen everywhere at all times for all types of fields. Electromagnetic fields fluctuate. Virtual photons appear and disappear. When you place two metal plates close together, you impose boundary conditions on these fluctuations. Certain electromagnetic wavelengths can't fit between the plates. The wavelengths are longer than the gap, so those modes are suppressed, excluded from the space between the plates, but they continue to exist in the space outside the plates. This creates an imbalance. More virtual photons pressing on the outside than on the inside. The net result is a force pushing the plates together. This is the Casimir effect. It sounds like science fiction, but it's real. It was first measured experimentally in 1997 by Steve Lamoureux at Los Alamos National Laboratory. He used metal plates separated by gaps of about 1 micrometer. The measurements match Casimir's prediction. Here's why this matters. The energy between the plates is negative relative to the energy of empty space outside. The Casimir effect created a region of negative energy density, exactly the exotic stuff that warp drives and wormholes require. It's not much. The energy density is tiny, and it only exists in the narrow gap between the plates. But it proves that negative energy isn't just a mathematical fantasy. It's a real physical phenomenon, observable in laboratories. The question is whether we can scale it up. Can we engineer negative energy in bulk? Can we shape it into shells and throats? Can we manufacture enough of it to bend space-time on demand? We don't know. But for the first time in history, we have the mathematics to describe how to ride a wave through the stars using ordinary matter. We have the theoretical framework. We have the software to test it. And we have proof that the universe allows negative energy to exist, even if only in microscopic amounts. The wall is still there, but now we know where the door is. And somewhere in the equations, the key is waiting. 1,000th of a millimeter. That was the gap. In 1997, Steve Lamoureux placed two uncharged metal plates that closed together at Los Alamos National Laboratory, and he measured the attraction pulling them together. Since then, the effect has been replicated in labs worldwide with increasing precision. Modern experiments detect these forces with exquisite sensitivity. Here is why this matters. The space between those plates has lower energy density than the vacuum outside, lower than empty space itself. By definition, that is negative energy, not a mathematical trick, not virtual particles flickering in and out of existence. Actual, measurable, persistent negative energy, the only confirmed example in all of physics. The Casimir effect proves that negative energy is not forbidden by nature, at least not in small amounts, at least not under specific conditions. The question is scale. Can we produce enough to power a warp drive? The math is brutal. A pair of plates 1 square meter in area, separated by a gap of 1 micrometer, produces total negative energy on the order of 10 carat minus 7 joules, 1/10,000,000th of a joule. That is less energy than it takes a mosquito to flap its wings once. Warp drive designs call for negative energy measured in kilograms or tons of mass equivalent. Using Einstein's E equals mc squared, 1 kilogram corresponds to roughly 9 times 10 carat 16 joules. The gap between what a Casimir cavity produces and what a warp drive needs is approximately 24 orders of magnitude, a factor of 1 trillion trillion. Nevertheless, the Casimir effect appears in every serious warp drive paper because it proves the concept. Negative energy can exist. It exists in laboratories right now. The question of scaling it up is a question of engineering. Extraordinarily difficult engineering, but engineering, not fundamental physics, saying no. Several speculative proposals attempt to bridge that gap. One idea involves stacking thousands or millions of Casimir cavities, hoping the contributions add up. But cavities interfere with each other electromagnetically. The vacuum fluctuations couple through the geometry, and the gains diminish rapidly as you scale up. Different spacing patterns, different materials, different shapes. Nothing has yet produced a breakthrough. Another approach involves the dynamic Casimir effect. If you oscillate the plates rapidly, shaking the quantum vacuum hard enough, you convert virtual photons into real ones. In 2011, researchers at Chalmers University in Sweden demonstrated this using a superconducting circuit mimicking a moving mirror. Real photons emerged from the vacuum. It was a landmark proof that the quantum vacuum can be manipulated to produce particles and energy, but the power output was faint, unimaginably tiny fractions of a watt. Scaling this to warp drive levels will require oscillating massive structures at frequencies that would tear them apart. The materials do not exist. A third avenue explores other quantum fields beyond electromagnetism. The electron field, quark fields, the Higgs field. Each has its own vacuum structure. Perhaps one produces stronger negative energy when confined. The calculations push modern supercomputers to their limits, but so far, no configuration has yielded dramatically better results. The numbers remain stubbornly small. There's also a theoretical constraint called the quantum inequalities, proven by physicists Larry Ford and Thomas Roman in the 1990s. These theorems show that negative energy comes with strict limitations. The more intense a negative energy, the shorter it can persist, and the smaller the volume it can occupy. You can have a lot for an instant or a little for a while, but you cannot have large amounts sustained indefinitely in a macroscopic region. Exactly what a warp drive would need. These inequalities do not absolutely forbid warp drives, but they make building them from quantum vacuum fluctuations extraordinarily difficult. A loophole might exist in quantum gravity, the unknown theory that unifies general relativity with quantum mechanics, but that remains speculation. All of these approaches remain active research areas. Small teams at universities and national labs make incremental progress, measuring smaller forces, understanding the physics more deeply, but none has produced a practical reservoir of negative energy at the scales required. The engineering challenge is immense. It might remain immense forever, or it might yield to some future insight we cannot predict, which means that on the longest timescale, warp drive might not require entirely new physics, just extraordinarily patient refinement of the physics we already have. But if warp drives exist anywhere in the universe, and if they occasionally fail, we might be able to detect them. In 2024, Katie Clough and collaborators at Queen Mary University of London published a paper in Classical and Quantum Gravity titled, "What No One Has Seen Before: Gravitational Waveforms from Warp Drive Collapse." They asked a question nobody had seriously addressed. What happens when a warp bubble fails? Not how it might fail, but what observable signature it would leave that a warp bubble is structured space-time held together by matter and energy. If that distribution becomes unstable, the bubble collapses violently. The curved geometry suddenly relaxes back to flat, releasing all the stored energy. Clough's team used numerical relativity, the same supercomputer techniques used to simulate black hole mergers for LIGO, to model this collapse. The bubble imploded, and as it died, it emitted gravitational waves, ripples in space-time propagating at light speed. The waveform was distinct. A brief burst of high-frequency oscillations followed by a ring-down, different from merging black holes, different from neutron star collisions, a unique signature. For a bubble a few miles in diameter, the dominant frequency would be around 300 kilohertz, far above LIGO's detection band of 10 hertz to a few kilohertz. Even if a warp drive collapsed in our own galaxy, LIGO would not hear it. But future detectors could. Proposals for high-frequency gravitational wave observatories, using superconducting resonators, levitated sensors, microwave cavity arrays, are in development. If they achieve projected sensitivity, they would open a new window on the gravitational wave sky. With warp drive collapses as a candidate signal, this offers a tantalizing implication for the search for extraterrestrial intelligence. Traditional SETI scans for electromagnetic signals, radio, lasers, waste heat. But if advanced civilizations operate warp drives, and if those drives occasionally fail, the gravitational wave signatures would propagate across the cosmos. By searching for specific waveforms predicted by warp bubble collapse, astronomers could potentially detect not just the existence of aliens, but evidence of their advanced technology. The probability chain is long. Civilizations must exist. They must use warp drives. Those drives must fail often enough, and we must be listening with the right instruments. The product of these uncertainties is small, but not zero. Even if nothing is found, the search places constraints, limits on how common warp-capable civilizations are, and the modeling has immediate scientific value. By simulating warp bubble collapse, Clough's team developed techniques for exotic space-time geometries that apply to black hole interiors, the Big Bang singularity, and cosmic strings. The tools for one problem find applications elsewhere. The hunt for faster-than-light travel, even if it never succeeds, produces scientific progress as a side effect. Which brings us to the honest question. Where does this actually leave us? What the mathematics says yes to is significant. Warp drive as a solution to Einstein's field equations has been valid since Alcubierre's 1994 paper. 3 decades of refinement have not invalidated the core concept. What the mathematics also says yes to, based on applied physics work, is that warp drive does not necessarily require exotic matter, at least not for subliminal designs. The Fuchs 2024 paper demonstrated a warp bubble, using only ordinary positive energy, satisfying all classical energy conditions. This moves warp drive from pure theory into the realm of plausible engineering. Not engineering for today, not for this century, but engineering consistent with known physics. What the mathematics still says no to is faster-than-light travel without exotic matter. Every superluminal configuration identified so far violates at least one energy condition. The light barrier might hold for warp drives just as firmly as for rockets. What the mathematics is ambiguous about is everything in between. Whether Casimir effects can be scaled up, whether new physics provides loopholes, whether undiscovered mathematical approaches reveal solutions we have not found. These questions might remain open for decades, centuries, or forever. The gap between theory and practice is closing in one sense. We understand a problem better than in 1994. Warp Factory lets researchers evaluate designs numerically. Numerical relativity models failure modes. Gravitational wave observatories might search for alien warp technology. This is real progress, real tools, real research programs. But the gap is not closing in the sense of being near a working vehicle. The energy requirements for even subliminal warp drives remain beyond our civilization's capacity. We are talking power outputs comparable to significant fractions of global electricity generation, sustained for days, focused into matter shells that must maintain shape under stresses thousands of times higher than our best alloys can handle. We are centuries away from that capability. The instrumentation for testing small-scale effects does not yet exist at the required precision. Before anyone builds a starship, someone must demonstrate the effect in a laboratory, measure tiny space-time curvature around benchtop experiments. We can detect gravitational waves from black holes billions of light years away, but measuring static local curvature from a small mass distribution remains unsolved. For a mission planner, the assessment is clear. Warp drive is real as a physics concept. It is plausible as a long-term engineering goal. It is not imminent as a technology, not this decade, not next, not this century, probably not for several centuries. The interstellar voyages of science fiction, ships hopping between systems as casually as airplanes cross continents, remain fantasy. But fantasy is not the same as impossibility. A fantasy violates fundamental laws. A long-term engineering goal is consistent with known physics. Hard, yes. Expensive, yes. Distant, yes. But not forbidden. Warp drive clears that bar. Narrowly, with caveats, but it clears it. The research community continues building on that foundation. Papers appear every year. New designs are proposed and analyzed. The solution space expands slowly. Humanity may never leave the solar system with warp drive. Our civilization might collapse before we develop the technology, or we might find that some deeper law of physics forbids it after all. But the alternative is also possible. On some distant century, a research team might crack the final problems, build the first test bubble, demonstrate that it works, scale it up, and humanity lights up a warp drive for the first time, crosses the Proxima Centauri not in 70,000 years but in years, reaches Sirius, reaches Vega, spreads across the local stellar neighborhood. The mathematics says this outcome is not forbidden. The engineering says it is not close. The honest verdict is patience. The honest strategy is to keep working, one equation at a time, one experiment at a time, one refinement at a time, because the distance to Proxima Centauri is 25 trillion miles, and a species that walked on the moon, landed rovers on Mars, detected gravitational waves from merging black holes billions of light years away, and photographed the event horizon of a supermassive black hole does not give up on a problem just because the numbers look hard. The mission brief ends here. The equations are written. The simulations are running. The instruments are being designed. And somewhere in the future we cannot quite see yet, the first warp bubble might be learning how to bend space itself.